Good morning, good afternoon, good evening, everyone. Welcome to our workshop on building anomaly detection systems with TinyBird. This will be part presentation, part coding session. My name is Jim Moffitt. I'm a developer advocate at TinyBird. I've been working with the platform for about a year now. And I got to say, it's a great product to advocate for. I just love all the different things you can do with it. The mission of building APIs can be a difficult one, and TinyBird makes it quite easy to do that. In this session, I'll be providing background for developing real-time detection for 5 different types of anomalies. And then we'll check out how these anomalies are implemented using TinyBird. And one key takeaway is that the 5 methods we discussed today, they can all be implemented in SQL. And assuming we have enough time, we'll add these anomaly detection methods to an existing project. The great thing about anomaly detection, in my mind, is that by definition, it's all about identifying events of interest. Regardless of your data domain, anomaly detection is likely to be a very useful tool for you. For over a decade of my career, I focused on anomaly detection. I spent 13 years developing flood warning systems, and these systems are all about applying anomaly detections. These systems that I worked on were designed and deployed to identify weather events of interest. And here we're looking at a project I built on TinyBird. What this thing is, let me go back. What this thing is it collects data for 175 US cities, basically based on population. This data comes in about every 10 minutes, and I've been collecting data for about a year. This is just showing what's happening here is this dashboard is making calls to TinyBird every 5 seconds to refresh the data. And here, let's talk about some of the session resources for today. One, you probably received an email and it had a link to this document. It's our getting started document. In here, you're going to find links to, the most important thing here is probably links to different tutorials. There's a tutorial for each anomaly detection method that we're going to discuss today. So if you have that document, it's good to have it handy so you can quickly find those resources. We also have a GitHub repository, which I will show here. This contains everything related to this project, including a data generator that was built for this. I'll probably talk more about that later. And again, most importantly, it has a set of tutorials. When we get into the different types, we're going to talk about 5 different types of anomalies, and each of these will walk you through. I'll show you one. The one that we're going to start with is the outer range method. But what these do is they show you how the endpoints were set up to exercise these detections. It also talks a little bit about how do you design the underlying algorithm with SQL. And then it walks through the actual building of these data pipelines that apply that SQL to detect detections. And we'll refer back to this as we move through the content. Another important thing in that repository is there's a TinyBird folder. And if you're familiar at all with TinyBird, you know that under the hood, as you build a project, you are building a data project which contains different resources. For example, each project will have 1 or more data source definitions. This project involved 3. Also, the pipes directory is a very important directory here. And we can refer to these as we move through the different methods. But again, like for the outer range, there's a pipe that's built to make those type of detections. And what these bring to the table, these files, that you can import them into any existing data project you may have. You will have to update the the schema attributes that you're referencing. For example, in this project, my timestamps are under the attribute timestamp. You may have a different name for your time field. It might be time, might be date time, what have you. And also the data that's coming in for this project from the data generator is the value is called value. But in other cases, you'll have different names for those data points that are arriving. For example, if we have time, I'm going to apply these anomaly detection recipes to a weather project, the one that we're seeing here. And in this case, for example, the temperature, it comes in with a data attribute name of temp underscore F for Fahrenheit. So as we apply these generic recipes to new data projects, you will have to update how you reference the different fields. And we'll get more into that in a bit. The goals for this session are, I want to set the stage by reviewing what TinyBird is and what are its core objects and what its underlying data store layer brings to anomaly detection. I want to review these anomaly types and the detection methods themselves. And we're going to add anomaly detection to an existing weather monitoring system. So why would you want to build an anomaly detection system? Well, first, if you're already a user of TinyBird, you probably already have data sources set up, and you may want to start scanning them for anomalies. And that's one of the points of this workshop is given these algorithms, these recipes, you can take them and insert them into your own workspaces and start scanning your own data streams for these types of anomalies. Another reason is you have a use case where anomalous events are of interest to you. And I put a smiley face here because the whole point of anomaly detection is surfacing events of interest. And regardless of your data domain, you're going to have events that are interesting to you. You can imagine like prices of stocks coming in to a system. Anomaly of interest may be a rate of change over a single set of prices, or maybe you're seeing an upward or downward trend as defined by statistical methods. Maybe you have a sensor that just has stopped reporting. That's a key one in many cases. I mentioned my background in flood warning. One example there is timeouts. Anytime a sensor out in the field stops reporting, whether it's raining or not, you want to know about that. Another reason why is like you probably have sensors that are reporting time series data. And what is a sensor? This entire project was developed with a set of sensors that emit or transmit real-time data. Maybe they're weather sensors, maybe they're stock prices. Sensors may measure actions taken on your website. The sensor may be transmitting game scores or other ranking attributes. So regardless of the type of data you're working with, I'm a big believer that this anomaly detection area should be an area of interest to any of us who are working with data streams. So now let's talk a little bit about the how. First, we're going to give some context about what TinyBird is. You may be familiar already. If you're not, I'll just spend a few minutes kind of studying the context of what TinyBird is. And in this case, why it's particularly an interesting tool for building anomaly detection systems. One, it has an OLAP database as its data layer. Now, specifically, we use ClickHouse as our data engine. And ClickHouse brings three important features to TinyBird. One is simply the ability to ingest massive amounts of data in real time. ClickHouse was built from the ground up to work with streaming data, and as such, TinyBird is designed from the ground up for working with massive amounts of real-time data. Another important ability that it brings to the table, and probably equally important, is the ability to serve thousands and thousands of concurrent connections and requests for data. This is a bottleneck with most more traditional data stores. You hear about some major enterprise grade data stores that maybe can handle dozens of simultaneous connections. Well, with TinyBird, we can serve thousands and thousands of requests coming in per second. Another interesting thing that TinyBird brings to the table, and this is particularly relevant for what we're discussing today, is that it has its own additive SQL dialect, including a large collection of SQL functions and clauses that make working with real-time data much more convenient. And we'll see many examples of this as we work through our different algorithms. Another thing that TinyBird is, in my mind, is it's a data platform for unifying data sources. You may have one or more Kafka streams. You may be ingesting PubSub streams. Maybe it's Kinesis from AWS. But you may also have lots of dimensional data. Maybe you have data stored in BigQuery or Snowflake or S3. Well, TinyBird makes it super convenient to pull those sources into your TinyBird workspace. So it's a common use case to have a live streaming, a set of live streams that you're enriching with dimensional data that you have stored elsewhere. TinyBird is also a data analysis platform. In our case, we are using SQL to join these different data sources, to aggregate them, to filter them. And along with SQL and certainly the ClickHouse dialect of that SQL, you can do some really complicated and advanced analysis in real time with massive amounts of data arriving. TinyBird is also a place to design and deploy API-based data products. And this is what really caught my eye when I first learned about TinyBird, the fact that it's essentially you can provide APIs as a service. Now, my background is mainly in weather collection, data collection, analyzing that data. And the fact that, me as a data engineer or as a software developer, I can do my analysis using SQL. I can click a button and I can host that as a very performant, low latency, high concurrent API endpoint. Kind of blew my mind. And it's just a wonderful place to design, but probably more importantly, to deploy production-ready API data products. So here's another view of what TinyBird is. Here we have an architectural schematic of a real-time streaming system. This is what a Kafka-based system would look like. And here we have an emitting data source that's generating events. In my case, for this project, it's emitting, sensor data in a time series fashion. That data is being generated. In the Kafka world, you have this event bus that's managing incoming topics on, one or more topics coming in, but it's also aware of who's listening, who's subscribed to those topics and doing the work of marshaling those events to the appropriate listener. And then you have the event listener that often gets loaded into a real-time database. It may get loaded into other databases at the same time, maybe into a data warehouse, something like Snowflake, who knows. And then once it's in that real-time database, which again, for TinyBird, that real-time database is implemented with ClickHouse. Often what comes with that, and certainly is the case with TinyBird, is you get a SQL engine. It's a way to query that incoming data using SQL. And the cool thing about that is, probably everybody who's watching this today probably knows quite a bit about SQL. And to me, it's pretty amazing that we have this syntax, this language that's been around for many, many, many decades, and that it's still so relevant and powerful, especially in this day and age of increasing amounts of data, increasing amounts of real-time use cases. And then on top of that SQL engine, you have a publishing layer. And in the case of TinyBird, we publish the data that you've analyzed and prepared as API endpoints. So TinyBird abstracts and encompasses the components in this purple box. So the topics that we're going to discuss in the next, in the next 45 minutes are, um, we're going to go through obviously the anomaly types that we're working with and talk about the algorithms that are implemented to exercise those detections. We're going to be implementing algorithms with SQL. We're going to be showing and building detection pipes. These are pipes that are set up to implement each detection method. And then this is all about publishing these as APIs. And it's worth noting at this point that since we are building API endpoints, it's important to note that the anomaly detection system is based on pulling these endpoints to see if anomalies have occurred. So you can imagine calling these endpoints every few seconds and scanning any data that has arrived since the previous pull. So now let's get into the anomaly types that we're going to be working with today. And these generally go, go from the most simple to the more complicated. First, we have auto range. This is the most simple method, and we'll talk about this one in more detail in just a second. We have timeouts. Timeouts are critical. Any sensor system you have, could be in manufacturing, could be vehicle information. In my history, it was weather data. You want to know when a sensor has stopped reporting on its expected interval. And also rate of change. You want to know if some reading has spiked since its last reading. And it's worth noting that the timeout and rate of change anomalies they're very conceptually simple, as you'll see in a minute, but I will say they have SQL implementations that are more complex than initially expected, certainly more complex than I initially assumed when I started this project. Next, we have interquartile ranges. This is a statistical based method. We also have the z-score method, another statistical based method. And these are very similar to each other. They're very similar with respect to their SQL structure. They both show how common table expressions bring a lot of logic power to building these algorithms. And they really show kind of they just show off how SQL can really get quite powerful when you start using CTEs. So let's start with our most simple algorithm. The auto range algorithm is the most simple in both concept and also in its SQL implementation. It's so simple that the SQL you see here is really all you need to know about implementing this method. I mean, in an operational system, of course, the next version would have support and logic for applying only one of these thresholds. In this case, we're checking each value with a maximum and a minimum allowed value. And in some cases, you might just have a minimum threshold. In many cases, you may only care if a value exceeds some threshold. And of course, you're going to have a bunch of sensor networks where there is, in fact, a valid range of incoming numbers that you expect. And an example from my flood morning days was having river level sensors that had a pretty narrow range of physically possible values. You may have a section of river where, yeah, it could go down to zero in an extreme drought, but it could only say go over 20 feet. It could not go over, say, 20 feet just due to the shape of the channel. In fact, most weather sensors have defined mins and maxes, which are key for working with data that have a lot of noise. In the systems I worked with, the data was first transmitted over radio. And that's just a channel where it's notorious for noise and collisions of reports. So this min and max, even though it's such a simple algorithm, was so key to just knowing and reducing noise in our data sets. And the power of this method is just knowing that these anomalies can be detected in real time, regardless of the volume and the velocity of the data coming in. Since all of the methods we're discussing today are based on SQL, this is a true statement for all of them. Here's a quick view of what this type of detection could look like. Here we have some sensor that has a pretty pretty normal steady state of values, but in this case, two values showed up that were clearly out of range. And the red dots indicate when those detections were made. Now let's talk about timeout anomalies. Now, conceptually, this is another very simple technique. Most sensors have some interval they are expected to report on. And this algorithm really has two steps. First, you look up the most recent sensor report for all the sensors in your network, and then you test them against some timeout duration. And the key thing here, again, is with remote sensors especially, most have a way to send a report to confirm their health on a mutually agreed interval. An example from my background is like rain gauges. They're only sending real rain data when it's raining, but at the same time, they are programmed to send in what's called a heartbeat report every half an hour or every hour. And that way you can listen for those heartbeat signals, knowing that the thing is still online and ready to report when it does rain. But if that heartbeat goes away, that can trigger proactive maintenance. And, it's really an important type of anomaly detection. You can imagine a factory floor where you have tens of thousands of sensors. To be able to know within seconds when one has stopped reporting is obviously a very powerful tool. So the interesting thing about timeouts in my mind is that it actually is kind of challenging with SQL. The challenge is retrieving a set of the most recent reports. And our first example and this type of anomaly is our first example of how ClickHouse SQL, how its dialect really helps. So here we're going to walk through a very basic SQL statement. And what this one does is using a ClickHouse dialect, it does easily retrieve the most recent report for a set of data. So in this case, I'm selecting everything from an incoming data source, which in our case is a live feed of sensor data coming in. And we're going to order that by timestamp. We're very biased. We want to know the most recent report for each one. And then this is the magic line that is provided really by ClickHouse, this limit one by ID. That helps us bring in the most recent report for any given unique ID. Just to give you some perspective, this is what that SQL could look like without using this function provided by ClickHouse, where it's just more complicated. You're doing a join, you're using a max function to find the maximum timestamp for a set of sensors, and you're joining that to find the most recent. So, this is very doable if you're not using ClickHouse, but it just kind of illustrates some of the value add that as TinyBird that we see from using a database like that. And here's a graph of what this type of anomaly detection looks like. It's kind of hard to tell, but basically we had a well-running sensor and all of a sudden it stopped. In this case, I was setting up I expected a sensor to report every 10 seconds. And as soon as that didn't happen, that detection is noted. Now let's talk about rate of change anomalies. This is our third of the 5. And this one is another example where it's a super simple concept. You're just, you're looking at time rate of changes. You have timestamps along the x-axis. The value that you're receiving is the y-axis. You have these 2 points. The rate of change, obviously, it's also referred to as slope. And that slope is equal to the difference in the y values divided by the difference in the x values. But it's a simple concept, but gets quickly into more complex SQL. In this SQL I'm showing, it's using ClickHouse window functions to find those previous values. It's all about retrieving that previous value for reports. And this is particularly important for sensors that are just reporting on random intervals. And it can take a lot of work and time to retrieve previous reports for sensors that do not share common timestamps on a given interval. And here again, we are using ClickHouse window functions to pull those values. The previous timestamps and values immediately before the current values that just reported. And this is used to calculate the slope between two sequential reports and flagging out rate of change anomalies. Here's two different views of this algorithm in action. The one on the left is a time series where we had one dramatic drop that, in this case, the rate of change was higher than what we nominated as our threshold. And you can see as soon as that report shows up, basically within milliseconds, we could know about that change, that rate of change anomaly. And the second plot on the right is also just to illustrate, this also works for these out of range type scenarios where you get a first detection when the sensor jumped out of range. That, obviously resulted in a rate of change that was excessive. And then when the sensor returned the normal behavior, we got a second event when that, in this case, it was a negative slope that was outside of the bounds of what we expected. And now next, we're going to get into the interquartile range type of anomalies. And this is a statistical based method. This method introduces a statistics time window where statistics are generated for a specific period of time. In this case, the quartiles are found, and the Q3 and the Q1 values are used to create a data range. So, and when you subtract the Q1 from the Q3, you get this IQR. But there's also a multiplier that is used, and this is very common. In researching the background of this method, I found that 1.5 is a very common multiplier to use to define the final range. So here we're looking for values, anything that's larger than the Q1 minus the IQR times 1.5, that's considered valid. And same, any values that are under the Q3 plus this buffer of the IQR times 1.5. So it gives you this range that's considered valid. And anything outside this range, of course, is flagged as an anomaly. And this method, along with the z-score that we're about to talk about as well, it shows the power of the common table expressions that you can use in SQL. Here's a look at what that can look like. What we're seeing here is we are in this with statement. We're setting up a stats data object essentially, and within that scope, we are looking for, and this is again using ClickHouse methods for extracting these quartiles. We're extracting the Q1 in that second line there. We're also extracting the Q3, and then we're doing this. We're setting up the IQR as the difference of those times 1.5. And we're applying this for any data that has arrived in the last 30 minutes. But the key thing here is that above that with block, what it's doing is it's setting up the statistical parameters we need to apply the method. And that is referenced down below in the main body of this query, where we're referencing the stats object. And this will be a pattern that you'll see in both this interquartile method and also the z-score. What's cool about this one is that you could imagine if you tune the statistics method and you tuned the multiplier that you're using, that you could that the rising pattern here could be detected maybe sooner or maybe more often. The key point is that with the statistics window, in this case, I think I was using, looking back for the last hour, But also that multiplier, you can really fine tune your algorithm to match your data, to match the patterns that you're seeing, to make that algorithm more or less sensitive to trends. And what I liked about this is like it started to, up until a certain point, the upward trend was well within the interquartile range of expectations. It fell within that range, but then you got 3 points in a row that were above and beyond that. So it's a really interesting way to detect patterns that all of a sudden become unexpected. So next, let's talk about z-scores. So here, z-scores are very similar to the IQR. They're similar in that they also use a statistical method. In this case, we're using that stats window for calculating an average and a standard deviation for the time period. And the z-score is a pretty simple equation. It's just the value that you're analyzing minus the average of that window we just talked about, and then divided by the standard deviation of that same period. And then you after making the z-score, you decide on some threshold that anything above that threshold are marked as an anomaly. And I'd say the general convention here is to set a z-score of, say, 2. So any data point that comes up with a z-score above 2 or below -2 is marked as an anomaly. And it's another example where by adjusting that statistical window, you may have pretty stable data where you can do a statistical window of maybe several hours, but you may have very erratic data where you really want to just track and build these statistics based, maybe on the last 1 hour or even 15 minutes. And along with that, you can fine tune the threshold of the z-score that makes sense for your data set. I found that using the z-score too is actually quite useful, but you may have your own situation where you need to tweak that value. Maybe it's 3, maybe it's 1.5. And that's the beautiful thing about when it comes time to define your endpoints that implement these methods is you can set those type of things up as request parameters. So you as a user of the API, you can on the fly, you can adjust your statistical window. You can also adjust your z-score threshold. And the same goes for these other methods. I mean, one example would be with the timeout method. You might have sensors that you expect to literally to report every second. So you could set a threshold of 1.2 seconds or 3 seconds. But you may have other sensors where, they're only programmed or automated to send in a heartbeat every hour. So you could set your timeout accordingly. I do want to mention we've blogged about the z-score world before. I'm going to open up this. My colleague Alberto wrote this back, coming up on 3 years ago. But he wrote this blog post about doing these simple statistics for anomaly detection on top of time series data. And then I got to say, this blog post was kind of the initial inspiration for the rest of this work. So kudos to that. And again, here's a view of again, I have this data generator that's just sort of spitting out random data. And this was a case where using, again, I think it was a 1 hour statistical window and a z-score of 2, where it did detect these 2 points as anomalies. And again, I find it really interesting because this is a very erratic sensor in a way. And it took a special pattern of increasing to match that statistical scenario where the z-score was out of range. All right, so now let's get into and actually see actual code of how these were set up. What I'm going to do is I have an anomaly detection workspace. And here, let me log in. And if you're familiar with TinyBird, I'm going to go to what I've done is I set up this workspace to actually build this project. I have a data source that's emitting sensors every few seconds. It's landing in a data source called incoming data. I cleared out the data last night and revved it up again. I have nearly 200,000 points in there now. I can come here and look at. Oh, I should mention this first. If you're new to TinyBird, we have this feature called Playground, and what it's pretty amazing because you can experiment, explore your data, explore your SQL. Here, for example, I was setting up using this limit one by ID type syntax that ClickHouse provides. I wanted to just test my initial query of looking up the most recent report from any sensor. You can see here, if I run this, first, you can see that these things are, I'm looking at my clock here, and all these reports just showed up in the last few seconds. I do see an exception here. In my data generator, I do have there's a way to say I want sensor X to stop reporting at some point, and I have that set to sensor 5. So you can see here where that sensor is not reported in quite a while. What else to talk about here? I won't get into this stuff, but in this system, I'm copying and I'm building a log of anomalies that have happened. So this is an ongoing record of all the different anomalies that have happened, and I'll show you what the data looks like that we're working with here. I have another Grafana dashboard, and this is the type of data that this data generator is producing. I have 10 different sensors. It's kind of a random number. I set this up to do 10. It is a lot of data. You can think of this data as like, well, I've used it in other workshops as sort of a proxy for stock data. You can call it what you want, but the whole point here is this data generator sends out every second, basically, reports from 10 different sensors. And with the data generator, you can prescribe different types of anomalies. You can say, hey, I want 5% of its reports to be outliers. I want 3% to be step functions that I can test these algorithms against. I already mentioned I want to be able to set up a sensor that simply times out. So this is kind of cool. You can see I set up sensor 5 to timeout. Sure enough, it was detected. It timed out. I don't know. That's like 40 some minutes ago, maybe. But here's what that data looks like. And you can see different patterns that you can test, whether this was maybe flagged as out of range, maybe a step function violation, what have you. But this is the data coming in to this TinyBird workspace. So those are the data sources. Let's dig it. Now these pipes are where the SQL that we've been talking about are implemented. Let's look at the the out of range. No, let's look at rate of change as one example. So this is where you apply these algorithms that we talked about, the SQL. So here I'm doing a select statement. I'm grabbing the ID of the sensor, the value. Again, this is the key sections for this algorithm where I am using these ClickHouse window functions to pull in that previous value and that previous timestamp. Now, if you're coming from the world of relational databases, given that ClickHouse is a columnar database where things are indexed by column, basically, where you have a time column, it makes this type of fetching data possible. Whereas with a relational database, each timestamp will have a complete row of data. And to find the most recent report for any given sensor, it's more of an exercise of finding out when was the oldest report for the set of sensors, pulling that full set of data, and then maybe using something like Python to iterate through each individual sensor to find its most recent. I mean, you could do a simple query where you're looking at pulling a query for each sensor and finding its most recent value. But in this case, we're doing this in one call across the whole set of sensors, and it's all through the magic of this ClickHouse Windows function. So here we're calculating the rate of change, and we get these values here. It's calculating a slope based upon that previous value, previous timestamp. Oh, I'm looking at the wrong one. But same thing. Let me go back. Rate of change. So this first node, this is where we're calculating the slope. It's the same SQL I just showed you. This first node will do what we just talked about. It'll find the previous values, the previous timestamps. It calculates the slope. And then in the second node, it's applying those slopes and testing them against our max slope that we are decreeing as our maximum slope allowable. And another one I want to show about these recipes that we're sharing. And again, all of these are available in this repository. Let me just go back for a quick tour again, orientation of what this thing is. There's a good introduction here, kind of introducing to the different types, talks about the data generator and the dashboard. In fact, the dashboard definition is a Grafana dashboard that's included in the repository. Yeah, there's a lot of good information here. Let me go back. Here we go. So again, this is a case, and one thing about TinyBird is when you build these pipes, you can build with one or more nodes, and these nodes are just where you put your SQL. And the key concept here is one node can build off another. So this is an example where our algorithm uses two nodes. The first one, as the name implies, calculates the slope. We've talked about that. And then this next one does the testing of all those slopes for the data that's just arrived and finding the one that is over our max slope. In this case, our max slope is set to 3. And I want to just briefly discuss these algorithms, these recipes that we're sharing. They all have this setup where you'll notice that if I go up here, that this endpoint that we've published, it has 3 different request parameters that you can come in with. One is the detect window in seconds. What that means is you're going to be pulling this endpoint maybe every 60 seconds, maybe every 30 seconds. Well, you can set, based on that interval, you can set this detection window, and that just defines how far back in the most recent data are we scanning for these anomalies. The other important thing for this one is you can set on the fly through the API what is the max slope that you care about. And this, right now, it's the default, and these defaults are set up here. Here we're using a default detection window of 600 seconds, so 10 minutes. And we're setting a default of a max slope of 3. And you can change these defaults, but more importantly, you can change them when you make each individual request. So that's how that recipe is set up. Let's go back to the auto range. This again was that more simple, the most simple SQL design. What's making this look a little bit more complicated is, again, we're building in support for flexibility for the user to make these calls. Again, we have a detect window seconds. Currently, this one's set up to default to 60 seconds. That's based on a premise that we're going to query this every minute looking for auto range values. Obviously, you can set a max value and a min value. And in this case, you can set a sensor ID. In our case, we have 10 different sensors. But regardless, you'll probably want to set up these endpoints where you may not care about the whole population of sensors. You want to have at least the option to query about a specific sensor. And this one matches that similar pattern I talked about. I can zoom in a little bit to this. But what we're setting up are defaults. This is a 60-second default, as I mentioned. I set up, these are just arbitrary at this point, but given your sensors and your known range of valid values, you would set these accordingly. I'm looking for values for anything that's less than 1 and anything that's more than 1,000, I'm going to say is an outlier. this whole block here is simply logic to support whether the user supplies one of those thresholds, both of those thresholds, or maybe they don't specify any threshold. If they don't specify a threshold, they will be working with these defaults. But if they are sending one, a max or a min or both, this handles the logic of how to test that data. This block here is using, again, our templating language where if they do define a sensor ID in the request parameter, that's where we drill down and we adjust our where clause to require that the ID we're pulling from our data store is equal to that sensor ID. And here's where we implement our looking back only that detection amount of time in seconds. So if I run this, we see that we have several that are out of range. If you're new to TinyBird, the cool thing about this is, in this case, I had a single node that I implemented my SQL with. And once, down here, I run it and I see the results I'm expecting. At that point, you just come up to this button, and I've already published it, and I can do it again. But just by clicking that button, I've now published this out of range method as an API endpoint. And I can come here and view that API. And you'll see here, it's got a nice auto-generated documentation about what my request parameters are. Here's example usage. This is pretty cool how you can come in here and it's using the defaults that's set up, and we have quite a lot of results, but dynamically I can come here and say, you know what, I'm just looking for any sensor that's over 3,000. I change my max value. I click on that and I see I didn't get any results, so I know that all of my, if 3,000 was my threshold, I know that all of my sensors are reporting as expected. Let's look at the timeout method. And again, we talked about this. So this one, it's a little bit different here. You just set the interval that you expect your sensors to report in. And you can also specify a sensor ID. That comes in handy if you have a set of sensors and maybe some have a expected reporting frequency of every second. Maybe you have other certain sensors that maybe you only hear from them every 5 minutes. Well, by setting these up as dynamic query parameters, you can adjust that as you make your requests. As we discussed earlier, the first step in this algorithm is pulling the most recent for every sensor. I'm going to run that. And you'll see most of these I've reported in the last second. And as expected, we still have sensor 5 that stopped reporting. If I run, then the next endpoint, again, is taking those most recent values. You can see here it's selecting from the previous node, which is called get most recent. It's pulling from those results, and then here is where it's testing to see if those sensors are beyond our threshold of this parameter that we passed in seconds. And if we run that, you'll see that, yep, everything is reported as expected except for sensor 5. We haven't heard from it in about 50 minutes. Let's look at the interquartile range. This is the one again where we have a common table expression. Actually, we have two, but here we're setting up our defaults. Again, here we're using 10 minutes as our default window. We're setting up our IQR multiplier of 1.5. That's sort of used by convention. But again, this is an opportunity where you can kind of fine tune that to your data sets. And here's where we have a new request parameter, the stats windows in minutes. And here I'm saying the default is we're going to do our stats. In this case, it's finding the Q1 and the Q3. And we're basing that upon the last 60 minutes of data. Again, if you have super erratic data, maybe that window, maybe you can shorten it. In some cases, maybe you could open up that window. Maybe it's several hours of how you define your lower and your upper quartiles. But in this here, we are setting this up as our stats data object. within this width block, we're going in and we are finding those quartiles. And then you'll see down below, we're referencing that stats data object. We're referencing the IQR that was calculated above. And we're setting up and showing the user what that lower and upper bound were. And then we're checking according to that detection window limit. In this case, I think we set it up for every 10 minutes. It's looking at just that data that's most recently arrived and checking on any outliers. And here, actually, we see a few that met that outlier definition. And then our final one to take a view of are the z-scores. And this is very similar in structure to what we just saw with the interquartile range, where we have this stats block. Instead of looking at quartiles, this time we're calculating an average and a standard deviation, and we're applying that over the stats window. In this case, we're working with minutes. Let's see, the default is 10. So we're basing this on a 10-minute window, looking at the average data value over that 10 minutes along with its standard deviation. And then we're referencing that stats down here. We're calculating the z-score based upon those. And we're looking for any that are above that threshold. No, that's not true. That happens in the next node. Here we're setting up the stats. We're setting up the data that we need to scan. And then down here in the endpoint, this is where you can see here, we're looking at for any new data point that is below or over, below the negative z-score or above the positive z-score. And you can see here in the current data that we're working with, we have only sensors that are below the z-score. And again, the z-scores can be, above the range of expectation or below the range. In this case, we're getting values that are lower than expected. So that's what all of this looks like in TinyBird. Now we got a few minutes left. One thing I want to discuss is, we provide these recipes. And again, I want to highlight the tutorials. If you're interested in implementing these methods to your own data set, this is where I would start. Each one, like the z-score, again, just to review, it kind of introduces how the algorithm is, what it's based upon. Talks about what we're building with this tutorial. In this case, we are setting up an endpoint with the following query parameters. Helps you understand just how it works. And then we get into the actual SQL that's used to implement this. First, we kind of do the most clean version that just illustrates the SQL algorithm, if you want to look at it that way. And then down below, we talk about actually building the end pipe or the endpoint. And when we do that, we talk about, what makes the endpoint more operational in the end. In this case, what that means is we're adding support for being able to set up these dynamic parameters for both the z-score threshold, for the detect window, for example, for selecting certain sensors of interest. And we talk about if there's one or two nodes, we talk about each one and what it brings to the table. We have a little checklist of the steps you need to take to implement this tutorial. We have some example requests and also example responses of what you'd get back. And then finally, we show these examples of when a detection was actually found. And the key thing here, when you get to the step of applying these to your own schema, is just that. You need to adjust your schema. The schema above is what this project, what this repository is based upon. It was based upon the premise where every sensor had a unique numeric ID, and the value that it was sending in was called value, just a float 32. Well, I wanted to go apply this to my weather detection system. Namely, I wanted to know if sensors stopped reporting. I wanted to know, certainly interested in the temperature world. I want to know, like, where in the country is it above 100 degrees? Maybe I'm agriculturally focused and I want to know where it's freezing, etc. But the schema that I used in that weather project was different. So it was site name. It was a unique string. In this case, it was the name of a city. And also, I had many different data values coming in, but one of them was temperature underscore F. So this is a case where if I wanted to apply these anomaly detection methods to a certain weather data type, I had to make these changes to the SQL that we just walked through. And I can show an example of doing that. So what we have here is just an empty workspace. I've used a feature that's available on TinyBird. I'm actually shared my underlying weather data with this project. And if I wanted to set up a pipe, I'm going to do, let's call one here. Let me bring up, I have some SQL I want to pull into here. So the exercise of converting these recipes to this project, here I'd set up a pipe. I'm going to call this Timeout. And I'm going to add a node. And just like before, I'm going to call this first node get most recent. And I'm going to copy in what this would look like for this project. And the thing, again, the point out here, everything's pretty much the same, except here I'm not selecting a numeric ID for that sensor. Instead, I have this thing called site name. In fact, I can click on this data source, so you can see the schema that this one uses. And you can see that I don't have anything called value, but I do have these individual temperature readings or weather readings I can reference. It's kind of my convention these days. I always have a timestamp called timestamp. So I didn't have to change anything there. But if I go back to this query, and this query is pulled directly from our repository. But again, I changed the site name. It used to be ID. And instead of pulling in value, I'm bringing in the parameter I want to build a detection for, and that's this temperature reading. But everything else is the same. And again, if I want to then finish this method for this new data set, I need the second node, which in this case I called endpoint. And I'm going to pull in some code and put that here, and we'll walk through what this is. And again, the only changes from what we saw before is this update from ID to site name, again, from value to temperature F, but everything else is essentially the same. And I can play with the amount of time that here I want to see what hasn't reported. Here I'm looking at what hasn't reported in 10 minutes. And I have a short list. I expect this data to come in every 10 minutes, but you can see that's not the case for 175 different stations. Some have lagged quite a bit. Some hasn't. Los Angeles hasn't reported in 20. But here in this new workspace, if I want to create this as my timeout method for this workspace, I hit create this. I have two nodes set up. I named it endpoint because that's the one I do want to publish. You can name it whatever you want. That's just my convention. And here I have that as an API. One thing to show, we just have a few minutes left. I often use Postman as a great way to test all of this. Here I have that timeout again. Here I'm set it up in Postman. I set up what queries I can use. I can look for any timeouts for Denver. I don't expect to see any. No, I did get a timeout. Okay, interesting. I didn't report for the last 14 minutes. But anyway, so that is our wrap up of our discussion of building anomaly detections. The beautiful thing is, as you've seen, there's 5 different common methods you can implement in SQL. So really, no matter what engine you're using to do your real-time processing, if you can use SQL, these apply to those. If you don't have a real-time analytics platform yet, I'm obviously biased, but I highly encourage you to give TinyBird a try. Again, some next steps. We have that repository. It has everything that we discussed about. Again, the tutorials are the ones that I would start with. The next step would be to add these algorithms to your own TinyBird workspace if you have them, and also to join our Slack community. Certainly, if you get into this and you have questions, we are happy to help you there. And I will say we have a very active community with some real power users who know everything about our product and are an amazing resource. And I want to thank everybody for coming. We'll have more of these workshops coming up. I have one coming up in June 11th. We're going to be talking about setting up real-time leaderboards and how to build other user-facing analytics. And that is it. So thank you. We'll see you next time.